Hello. Thank you, Abby and Ella. My name is Sydney Barok, and today I will be presenting my thesis, Compliance with EEXI Regulations for Post-Panamax Containerships. I would like to start by thanking my principal advisor, Professor Boyd, for his guidance and help throughout this thesis process. I would also like to thank my reader, Professor Gallagher, and my editor, Professor Harris, for their assistance in putting my thesis work into words over the past year. The objective of my thesis was to develop a plan to lower ship owners' energy efficiency existing ship index over the remaining lifetime of their vessel at the lowest predicted cost. It also was to establish a methodology that could be easily expanded to different ship types, sizes, and indices. A quick outline of my presentation today. I will go through the background of environmental regulations and methods of compliance, the importance of the post-Panamax container ship class in this analysis, then move on to the numerical analysis methodology, in which was foundational in creating my tool, and the resulting conclusions I was able to pull out of my tool. I will conclude with recommendations for future work. There are several preliminary regulatory documents publicized across the globe in concern with maritime greenhouse gas emissions. These approaches fall into three categories: design, operational, and fuel. Design indices are based on technical documents showing that a ship is built to a high enough standard. Operational indices combine design indices with the actual operational qualities of a vessel. The CII regulations fall under this category. Fuel indices purely consider the quality and quantity of fuel being burned. These are less common. My thesis focuses on a design index, specifically the Energy Efficiency Existing Ship Index, or EEDI. It is closely tied to another set of regulations called the Energy Efficiency Design Index. However, this is directed towards new builds. The ultimate goal of these standards is to reduce global greenhouse gas emissions across the entire fleet. A target of 70% reduction by 2050 from a 2008 baseline was announced in combination with the EEXI EEDI resolutions by IMO. For existing vessels grandfathered in to these regulatory frameworks, this is completed through phases where the emissions requirements progressively tightened. As of now, we just entered phase 3, or the current KIDAS regulatory threshold. This is the governing equation for these regulations, which basically sums down to grams of CO2 emitted over the transportation work in ton mile. There are several conversion factors in the prior equation to modify the index value to be applicable across all ship types. When looking at the background of green technology, in general, it can be divided into 5 categories: digitalization, hydrodynamics, energy, machinery, and aftertreatment. Digitalization encapsulates speed reduction, alternative routes, and changes to the existing vessel's operation. These are not long-term solutions, as ships would not operate at the full capacity, which would greatly impact the economics of shipping. However, speed reduction can be looked at as a short-term method to meet EEXI regulations and keep a vessel in service. Hydrodynamic solutions include hull coatings, hull form optimization, air lubrication, and cleaning. As I am working with the design index, quantifiable efficiency modifications are necessary to be presented in the technical document. So this category falls out of the scope of this index. Energy is the biggest focus of this index. The main goal is to push towards the future of fuel, so these regulations were formed around this idea. The objective of machinery alterations for environmental regulations is to increase the efficiency of a system, reducing the emissions by burning less fuel. While waste heat recovery is an effective measure to improve efficiency, it is not supported in the regulatory document. Other methods, such as battery hybridization, show little potential given the long voyage lengths of post-Panamax container ships. Within aftertreatment, carbon capture systems and storage are a promising method. Proposals have been made to the IMO to modify the EEXI framework, but this has not been rectified at this time, therefore unable to be considered in the analysis. In the end, the main focus came to alternative fuels or short-term slow steaming. The recognized alternative fuels are LPG, LNG, methanol, ethane, and ethanol, alongside traditional diesel gas oil, heavy fuel oil, and light fuel oil. This analysis circles around the post-Panamax container ship class. This class was selected because they are standardized vessels with widely publicize operational and design data that were necessary in the verification and validation of the tool. They also commonly fall on the borderline of compliance, making small alterations very valuable. A quick outline of the methodology of my tool. Inputs are collected on the ship in question. The inputs are checked to make sure that they fit within the Post-Panamax container ship. Then calculation pathways are selected based on the technology on board. Results are provided to the ship owner and recommendations for fueling is made. The data collection and inputs necessary are principal particulars, main and auxiliary engine data, additional technology, structural enhancements, and emergency backup fuel. The principal particulars include the length, beam, draft, and design displacement. The collection gets a little bit more complicated when collecting for the main engine. The figure to the right depicts the methodology and data collection for the main engine. For ships that are utilizing short-term slow steaming, the maximum continuous rating that's limited, or the MCR, should be input in the second row. The tool will then default using the limited MCR, even if an unlimited value is present. The top section should be filled out for the primary fuel, regardless of if a ship is dual or singular fueled. If only one fuel is present, the last few rows can be left blank. Additional information is necessary for the dual fuel to calculate the carbon output and conversion factors. Fuels can be selected from a drop-down menu, which therefore populates fuel characteristics throughout the rest of the calculations. In the red box above are the IMO accepted alternative fuels. The lower heating value, carbon content, and conversion factors are known values put out by IMO and are industry accepted. The filling rate, density can be altered as more information is known about the specific fuel being used and the systems on board. There is an option to alter the index value in the presence of shaft motors, commonly called power take-in systems, shaft generators or power takeoff systems, or the presence of other green technology such as solar panels. These calculations turn on if a non-zero positive value is present. If not, the calculation pathway is shut off. The IMO also allows reduction in EEXI for ships with enhanced structure. This is taken as a percent over the design displacement for the last certified inclining light ship before alterations were made. Due to the presence of volumetric capacity being necessary in deriving the final index capacity, emergency backup fuel is a necessary component. This is not present in all ships, but especially those running dual fuel tend to carry a more traditional fuel as backup given the experimental technology present on board. These inputs correlate to calculations behind the scene. The first step is validating the principal parameters. The assumptions made are only valid for this class of ship. This ensures that the output aligns with the expected IMO value. The fuel calculation track then chooses a calculation based first on if it's dual fueled or singular. It then decides whether gas can be considered a primary fuel and will derive the liquid gas weighted average coefficient if necessary. The new propulsive powering value is created from the alteration coefficient utilizing fuel used and backup fuel if necessary. This translates into an adjustment based on the presence of slow steaming, shaft generation, shaft motors, auxiliary engines, reference design speed alterations, and a calculated assumed capacity of the vessel. The last major component before arriving at an EEXI value for any vessel in this class is allowing coefficient correlation factors to readily change. A major simplifying assumption was made that no post-Panamax container ship was ice-classed or had ice-breaking capabilities. Beyond that, these coefficients are readily changed with the presence of energy efficient or green technology, regulatory limiters on capacity, or other specific design elements. The output results in a large data matrix in comparison to the attained EEXI reference. From there, a cost feasibility analysis selects the current optimal value, producing recommendations. Graphs are actively generated based on the weighted values. The cost analysis was created on the basis of reduction capability of the fuel and the viability of the fuel in marine commercial use. The emission reduction potential is derived from the difference in lower heating value from an HFO baseline. The cost of fuel is encapsulated by the initial cost, CapEx, and the operational cost, OpEx. The initial cost is based on research data, as most of these fuels do not have commercially ready engines available. The operational cost was assumed to be primarily fuel cost. The viability is established by rating the maturity, and infrastructure availability for these fuels. The future fuel will be the one first to market with the lowest alterations needed to ports. This combines to create weighted values to produce recommendations. The results are populated with a ship's attained, required, and recommended EEXI value. The attained value refers to what a ship is currently operating at. The required is the maximum value a ship can have and maintain compliance. The recommended value is what the same ship would have if it ran the recommended alternative fuel. The tool presents all these values and produces recommendations to either stay with the current fueling system or to switch to a new fuel. This video depicts the recommendation process of the tool in question. It begins with the input page, which has been truncated to only show the main engine inputs for simplicity. Only main engine data is altered in this example. As can be seen, the current calculation is running for only HFO. Afterwards, the analysis populates an attained EEXI value for this vessel. It can be seen that the required value is less than the attained under these conditions. Due to this, the tool is selected or suggested to switch to LNG. The second input represents if the same ship is running LNG with diesel gas oil as a pilot fuel. The attained value is less than the required, meaning under these conditions, the vessel is compliant. Therefore, no alterations are created, and it is recommended to stay with the current fueling. In conclusion, a tool was developed to recommend cost-effective ways to lower a ship owner's EEXI rating over the remaining lifetime of their vessel. The methodology has been made to be easily expanded to different ship types, sizes, and to include the CII index. It also was prepared to adapt to changes in the industry as more green technology comes about. While the cost analysis has not been fully completed at this point, the preliminary data has indicated LNG is the current most promising fuel for existing ships under this analysis. This can be attributed to the high maturity as it's already being used in commercial marine industries. Additionally, several ports already have infrastructure in place. For current ships under EEXI ratings, the fuel sought after does not have to be the final future fuel. This regulatory framework is set to reduce carbon emissions as the industry phases out older ships in the fleet. Also, in this analysis, the cost analysis quickly became the most challenging aspect. Data on cost is not readily available, especially on technologies that have not been invented yet. This was approached by making all cost data flexible so the tool can be readily adapted to technological developments. The most direct recommendation for future work is the expansion to other ship types or to the CII index. Also, an analysis on the design and operational indices on reducing global greenhouse gas emissions could be utilized. This would be a continuation of both my thesis and Bishop's from Webb's 2012 class. Thank you.